Okay, got that going. All right, so section 3.1 is continuity. We're going to be talking about continuous functions. So all of chapter 2, sorry, that's not 3.1, that's all of chapter 3. All of chapter 3, with the exception of the very last section, is just about continuity and continuous functions. The last section is to help get us going with derivatives. So section 2, the big focus of section 2 was understanding sequences and limits of sequences. In a similar way, the big idea of chapter 3 is understanding continuous functions. Now remember, what was a sequence? There was a function whose domain is the natural numbers. Right? It maps the natural numbers to the real numbers. And so we used A1 to represent the real number that 1 was mapped to, and we used A2 to represent the real number that 2 was mapped to, etc. Right? So now we're going to be looking at functions from any subset of the real numbers. This is no longer the natural numbers, it's just some subset of the real numbers to the real numbers. So we're still looking at real valued functions. All we're doing now is changing this domain from requiring it to be the natural numbers to now it's just a domain, whatever. We'll look at functions from any domain we want. And are we all comfortable with this notation? F is a function from some subset of the real numbers to the real numbers. We're good with that? And remember that it has to use the entire domain. F maps everything in D to something in R. It uses all of D and it maps it to things in R. It doesn't necessarily use all of R, right? Any questions with the notation before we just continue? Anything we need to be reminded about with it? All right, then let's move on to what we mean by continuous function. So here's our big definition for the chapter. A function f from some domain, some subset of the real numbers to the real numbers, is continuous at some point x0 in D, provided that whenever xn is a sequence in D, such that it converges to x0, then the limit of the image of the sequence converges to the limit, or the image of the limit of the sequence. This is very similar to what we did in 2.1 when we were talking about polynomials. If you go back to 2.1, what we did when we were talking about polynomials is we proved that polynomials were continuous at every point. That's essentially what we did. So this should seem somewhat familiar. Let's read it one more time. So we have a function from D to R. It's continuous at some point in the domain, x0, provided that whenever we have a sequence in the domain that converges to this point, then the image of the sequence converges to, the limit of the image of the sequence converges to the image of the limit point. Remember, x0 is the limit of the sequence, f of x0 is the limit of the image of the sequence. And you're comfortable with the idea that if x of n is a sequence, then f of x of n gives you a sequence. Are we comfortable with that, or should we see that real quick? We're good with it? Keep going? Okay. So, if f is continuous at every point in D, continuous at every point in its domain, then we say that f is a continuous function. So in 2.1, when we did all that stuff with polynomials, we proved that polynomials are a continuous function. That's what we proved. We proved polynomials were continuous.
Well, what exactly did we prove?
We proved that, so we had a polynomial, p sub n of x was our notation for an nth degree polynomial. So if I have some nth degree polynomial, I prove that if the limit of xn is equal to some value, I don't want to use x because I use it there, we'll just say a. If the limit of xn equals a, then the limit of p sub n, some nth degree, let's say p sub k, some kth degree polynomial, that way we don't get confused with the n there. So, you remember what it means for it to be a kth degree polynomial? So we said if the limit of x of n is a, then the limit for any kth degree polynomial of x sub n is equal to p of a. That's what we proved.
Oh, okay. Yeah. I see what you're saying now. Okay.
Yeah, we showed that for any convergent sequence you choose, any convergent sequence for any a, and any sequence that converges to a, this is true. That's how we showed that polynomials are continuous functions.
Because, and just to verify that the domain of a polynomial is all the real numbers, right?
Yeah, so if we think about p sub k, p sub k being a function from the real numbers to the real numbers, and we let a be any real number we want, any point in the domain, and x of n being any sequence in the domain that converges to a, then this is always true. Therefore, a polynomial is continuous at every point in the domain, therefore it's a continuous function because it's continuous across its whole domain. And don't get those two ideas mixed up. It's possible for a function to not be a continuous function, but still be continuous at some of its points. It's only a continuous function if it's continuous at all of its points. We proved that polynomial functions are continuous, meaning that they're continuous across their whole domain. Make sense? Yeah? No?
So you can be continuous at a point and not have a continuous function.
Yes. We'll look at an example of exactly what that would look like. We'll look at a continuous function, a function that is not continuous at a certain point, and then a function that's not continuous at any point, to help get an idea of them all. So first we'll do this one. So do a proof real quick that f of x equal to x squared minus 2x plus 4 is continuous. Now we could just say by whatever we proved in section 2.1 is continuous, but we'll do a direct proof. So proof that f from R to R by f of x equal to, what I say, x squared minus 2x plus 4, doesn't matter, just some polynomial. We're going to prove that this is continuous. So I need to show that for any point in the domain I pick, and for any sequence that happens to converge to that domain, that the image of the sequence converges to the image of the point. So 1, I need to grab some arbitrary point in my domain. Let x be, let's not use x, we'll use a again. Let a be any point in R, doesn't matter what it is. 2, let an be any sequence in R such that the limit of an is equal to a. So grab some point out of the domain, and then grab some arbitrary sequence in the domain, but all we know about that sequence is that it converges to our point. Right? 3. Then the limit of f of xn, not xn, an, is equal to the limit of, what is an? Or f of an, sorry. That's just going to be an squared minus 2an plus 4. Right? Why do I keep doing something? Good so far? The limit of this is the limit of this. Now what do we know? We know that the limit of the sum or difference is just the sum or difference of the limits, so we can break this up into 3 separate limits. This is equal to the limit of an squared, we'll just say, well, I'll write plus the limit of negative 2an plus the limit of 4, and this is equal to the limit of a product is the product of the limits. So the limit of an times an is the same thing as the limit of an times the limit of an. But we know what the limit of an is, just a. So that's a squared. The limit of a constant times a sequence is the same thing as a constant times the limit of the sequence. So that one is just plus -2 times an. And then we know that the limit of a constant is just a constant. So plus 4, which is exactly what f of a is.
Wouldn't that be -2a instead of 2an?
Thank you. Yes. Which is exactly what f of a is.
Oh yeah.
Therefore, it's continuous. Therefore, f is continuous. Any questions on that?
So how would you do, is it possible to prove a function is continuous, the subset of the real numbers, say maybe an interval, rather than all the real numbers?
Yeah, you could change the domain, so I could have a function that isn't continuous across all of R, but maybe it's continuous on some domain, some subset of R. Then yeah, I could define a new function that goes from the subset to R, and then that would be a continuous function. Right? And we'll see an example of exactly what we're talking about. But so we're good with this, no questions here. You feel like you could reproduce something like this? If I said prove that this function is continuous directly.
If it's that simple, probably, yeah.
Yeah, just as polynomial. If I gave you just polynomial, said prove this is continuous. You could do it. Without just referencing back to we proved all polynomial functions are continuous.
If you had a problem like that on the test, I assume you would have to prove it directly.
If I wanted you to prove it directly, I'd say prove it directly. And I would guess that I do give you problems like this. But I don't know. I'd have to go back and look at the test. Just a guess based off of what I know about myself. Okay. Let's do another one. Okay, so prove that f as a function from R to R by f of x is equal to 1 if x is greater than or equal to 0, and 2 if x is less than 0. Is continuous everywhere except at 0. So we'll prove that this function isn't continuous at 0, but it's continuous everywhere else. And what does this function look like, by the way? Maybe some intuition for continuity. If we were to graph this function, what does it look like? It's 2 for all x less than 0. So 1, 2, not including 2. For all x less than 0, it's 2. And for all x starting at 0 and going to the right, it's 1. So if you graph our function, it looks like this. Notice it has a jump. A continuous function, you think about as just being a smooth curve is the intuition typically given for a continuous function. So our other function, whatever it was, I mean, here's a parabola of some sort. Don't remember exactly what it looks like, but it probably looks something like this. Whatever it was continuous. There were no holes, no jumps. I could draw it all with just holding my pencil to the paper. And there's also no sharp curves. Oh, that's derivative. No, that's still continuous. Sorry, getting ahead of myself.
I have a question. So is the reason your definition attaches like a function that has a hole in it, is it because f of x naught is not defined, so you can't say the limit of f as x goes to n is f of x naught?
I'm missing your question.
I'm just trying to see how that definition makes sure it doesn't include a function with a hole in it.
Oh, so when we get to the epsilon delta criterion, we'll have a better connection for how pictures work, because if you go take a calculus class at a college, this is not the definition that you're given. You're given what's called the epsilon delta definition, and the reason that they give you the epsilon delta definition is because it makes more sense with the picture. So we'll reconnect it with the graphs to show you how it makes perfect sense when we have our epsilon delta definition. It's a logically equivalent definition. This book's going to call it the epsilon delta criterion because if it's true, then it's continuous. But one way that you can think about the intuition for why we can't have holes is, well, how do I want to say this?
You can't converge to a point that isn't there.
You can't converge to a point that isn't there. Yeah. But I don't know, I don't have a good intuition for it yet, so let's keep going with this and then we'll see if something occurs to me. Okay, so let's do one where we're proving it's not continuous at 0, but it's continuous everywhere else. So let f be blah 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 this function. We won't bother writing that. Okay, so how am I going to show that it's not continuous at a point? Remember, to show it is continuous at a point, we need to take a point in the domain and we need to show that for any convergent sequence you pick, that this condition will be true. So to show it's not continuous at that point, I need to find a specific sequence that converges to the point where this does not hold. So I'm looking for a counterexample at the point 0. So I need to find a sequence that converges to 0, but the image of the sequence does not converge to the image of 0. So what's the image of 0?
1.
1. With our function f of 0 is equal to 1, right? So I need to find a sequence. I need to find a sequence x of n such that its limit is equal to 0, but I also need the limit of f of x of n to not equal f of 0. So I need the limit to converge to 0, but I need the image of the limit to not converge to the image of 0. You with me?
That's not too difficult, right?
No, it's not difficult at all. What's the sequence we want?
Maybe -1 to the power of n over n.
Or just -1 over n.
Yeah.
-1, -1/2, -1/3, -1/4, -1/5, -1/6. We keep getting closer and closer to 0 coming from the negative side, but we're always negative.
I see.
So this sequence is always negative, so the image of this sequence is always
2.
2.
I see.
And the image of 0 is
1.
1. So this is always going to be 2, this is always going to be 1. So it doesn't work.
So when you look at any function and you say, is this a continuous function or not, how do you suddenly get to the conclusion, oh, it's probably continuous everywhere except 0, now I can prove that?
This had a jump at 0, which is obvious. Right?
Okay.
This was 1 everywhere to the right of 0 and 2 everywhere to the left of 0. If there's a jump there, it's not continuous there. So the intuition for continuity is, can I draw it without lifting up my pencil, draw the function? If that's the case, it is continuous. That's the intuition when it comes to graphing functions. Okay, so yeah, we can use this exact same thing. So 1. Observe that 0 is in our domain, comma, -1 over n is a sequence in our domain, and the limit of -1 over n is equal to 0. Okay, so we found a point in our domain and a sequence in our domain that converges to that point. Now I just need to show that the image of this does not converge to the image of this, and we're done. It's not continuous at that point. Right? Then 1 over n is just equal to the sequence 2. 2, 2, 2, 2, 2, 2, 2. Right?
Is your function on the inside of the sequence or the outside?
The inside.
Okay.
What is, so this is equal to f of negative 1 over 1, comma, f of negative 1 over 2, comma, f of negative 1 over 3, comma, dot, dot, dot. What is f of negative 1? Negative 1 is less than 0, so it's 2. What is f of negative 1/2? Negative 1/2 is less than 0, so it's 2. 2. Right? So, since this sequence is just 2, 2, 2, 2, 2, 2, 2, it's just a constant, which gives me that the limit of f of negative 1 over n is equal to 2. So then, the limit of f of negative 1 over n, I'll just put all in one line, is equal to 2, is not equal to 1, is equal to the f of 0. Therefore, f is not continuous. Not continuous at 0. Now we need to show it's continuous everywhere else. Right?
Well, that's not technically what your proofs originally said you need to do.
Yeah, I just write it down to make sure that I knew what I was doing. Right here. So it's not continuous at 0, but continuous everywhere else. Is what the book wanted you to do. Okay, so we showed it's not continuous at 0, now we need to show it's continuous everywhere else. So for every point that's not 0 in our domain, it's either a point greater than 0 or it's a point less than 0. Right?
Isn't that just two different sequences that both are continuous?
Isn't,
Because
Kind
it's
of.
not one big line, it's two different ones. So can't you just name the lines and show that they're continuous separately?
you could do it that way. So I could then say, let g be a function from,
One if x.
we can't quite do that because we don't have a proof that just because two functions are continuous, then when you stick them next to each other, they're continuous. You have the right thinking, and we know that it happens to work in this case, but we
So
don't
you're
have a
saying
proof to
f of
guarantee.
x is continuous?
I'm saying f of x is continuous everywhere except 0. Pick any point that's not 0, and it's continuous at that point.
Okay.
Right? Because we have this notion of being continuous at a point. A function f is continuous at a point, provided that whenever xn is a sequence, indeed, that converges to that point, then the image of the sequence converges to the image of the point. So if that happens to be true at a point, then it's continuous at that point. If that is not true at a point, then it's not continuous at that point. So we showed that this is not the case at 0. We're going to show that this is the case at any point that's not 0.
Okay, but that still means f is not a continuous function.
It's not a continuous function. That's correct. F is not a continuous function. So it's continuous, so remember that we made that point. A function can either not be continuous anywhere, be continuous at some points, or be continuous at all points. If it's continuous at all points, we call it a continuous function. If it's only continuous at some points, we just say it's continuous at whatever points it's continuous at. And if it's not continuous at any points, then we say it's not continuous anywhere. So this is a function. It is not a continuous function, but it is continuous at every point except 0. So it's almost a continuous function, if you want to think about it that way. Okay, so now we need to handle the two cases, x. So we know that we've handled the case where x is 0. Now we need to show that if x is greater than 0 or x is less than 0, then it's continuous at that point. Right? So now, let x in R such that x is, which one should we do first? Greater than 0? So let x be any point greater than 0, comma, and let xn in R such that the limit, let's use a's so that we don't get confused with our f of x for our function. So let a be any point in R such that a is greater than 0, and let a sub n be any sequence in R that converges to a. With me so far? Six. Since the limit of the function is equal to, or since the limit of the sequence is equal to a, and a is greater than 0, so draw a quick picture so that I can just make this leap and I think you'll be fine with it. So a is some point greater than 0, a, 0 is over here. A some point greater than 0, and I know that an is a sequence, whatever it does, it eventually converges to a, right? Which means it eventually gets within any small distance we want of a. There's an index in the sequence such that from that index onwards, we're always within that distance of a. That's what it means to converge to a, right? So if a sequence converges to a, then that means we can always find, thank you, we can find a point in the sequence such that from that point onwards, we're always within an arbitrarily close distance of a. All I'm getting at is that if an converges to a, then there is a subsequence of an that is all positive. If I just pick all the terms of an that happen to be in here, that's now a subsequence of an, and it's positive. You good with that leap, or I need to go through the process?
Say that again, please.
A is a number greater than 0. So, if we write out whatever a is, we have a1, a2, ... Starting at some point in the sequence, a sub n, I know that from here onwards, this sequence is always within some small distance, epsilon of a. Right? So starting at this index going onwards, all these points are within epsilon of a. Which means, from this index onwards, all my points are greater than 0. Right? So if I just start here and take all the points from this point onwards, I just created a subsequence. Right? And notice all the terms of my subsequence are positive. So here's what I want to say. Maybe I'm just over-explaining, you would have gotten the leap just to begin with. Since a is greater than 0, comma, there exists a sub n sub k, some subsequence, such that a sub n sub k is greater than 0 for all k in n, for every term in our sequence. N, like that. Since an converges to a positive number, it has a subsequence composed completely of positive numbers. Are you good with that, Lee? Am I over-explaining? Okay. You guys are dead today. What's going on? Then show it.
I've been responding.
Alright. So, since a is a positive number, then an must have some subsequence that is completely positive. Alright. And we know that if an converges to a, then all its subsequences converge to a. If a sequence converges, then all its subsequences converge to the same thing. So, since okay, then the limit of f of a sub n sub k is equal to right, but what's it equal to? What's the actual number it's equal to?
Oh.
They're all positive numbers.
One.
1. Every term in this sequence is just 1, 1, 1, 1, 1, 1, 1. This is a constant sequence. The limit of a constant is just the constant. You with me?
I'm not sure why we needed to do that. Why didn't we just prove that an is 1?
I can't say that an is always 1, because an could have had some negative numbers. But it has a subsequence that's just positive numbers.
How could an be some negative numbers when the limit of an is greater than 0?
So all we know is that an converges to a, and a is a positive number. So let's say that a is the number 2. 2 is a positive number. An is just a sequence that converges to a. So it could be something like negative 5 over n plus 2. So here's a sequence that converges to 2, but notice it starts out negative. The first number in the sequence is negative 5 plus 2 is negative 3. But as n gets really, really big, this term goes to 0, and so it's just 2. So an could start out having negative terms, but eventually there's going to be a point in the index where from that point onwards, all the terms are positive. Right?
Right, okay.
So we couldn't just look at the image of an, because sometimes the image of an is 1 and sometimes it's 2, possibly. However, we're guaranteed that since a sub n sub k is always positive, then the image of that is always 1. And now we know how to take the limit of it. We know how to take the limit of a constant sequence.
Yeah, but you said that the limit of a sub n sub k is equal to a. What does that have to do with line 7? Because, like, you clarified that right before you wrote line 7. I'm wondering if that has anything to do with it.
Because a is greater than 0, not the
Oh, so then that's going to give me my next step, right? That's going to give me that the limit of f of a of n is equal to 1. Because now this is just a subsequence of this.
So they converge to the same thing.
So they converge to the same thing.
Did we do a proof last week that if a subsequence converges to a point, then the wave sequence converges to the same point?
That's not actually true, is it?
Well, let's try it this way then. I see your problem because of the way that the implication arrow is pointing. Then the limit of f of an, whatever that thing is, it has to be equal to the limit of its subsequence f of a sub n sub k, which we know is equal to 1.
What I was asking is, I can't quite remember, did we prove that?
If this converges, all its subsequences, namely this, converge to the same thing, and what does this converge to? 1. So whatever it was that this converged to has to be 1.
So we just have to prove that that converges then, f of a and f of a sub n.
Prove that f of a sub n converges.
Well, it does. Right?
No, she's actually got a good point. How do so I know that if this converges, then it converges to 1. Okay, but how do I know that f of a n converges?
Can you have a convergent subsequence in a divergent sequence?
In a sequence that doesn't converge, yes. Look at -1 to the n.
Oh, yeah, yeah.
So that has a convergent subsequence even though the sequence itself doesn't converge. So I need to justify that f of a sub n converges. How do we justify that? Because I know it's composed of 1s and 2s.
You know that at a certain index, it's all ones, right? After a certain index.
Yeah. I mean, I know how to give you the intuition for it. I know, obviously, that there comes a point, since all the terms in this are positive, then this for sure converges to 1. But do we need to just show that directly? Or is there a way that we can say it? See if I said anything in here. If x of 0 is greater than 0, then there exists an index n such that x of n is greater than 0 for all n greater than that index. And the limit of f of x of n is equal to the limit of the subsequence is equal to 1 is equal to, and I can say it's equal to f of a. But how can I say that f of a n converges? Is there a nice way to say it?
Hang on, do we even need to know that it converges? Because what we're trying to say is that the limit of the image f of a n k equals f of a n.
You could.
What we're trying to ultimately prove, this is the ultimate part that we need. We need f of a n is equal to f of a. So I need to say that this thing converges, and I need to say that what converges to is that.
Then why did we even bring in the subset? Because we're going
Because-
down and then back up in some way?
So I now know that if this thing converges, then all of its subsequences converge to the same thing. And since the subsequence converges to 1, then if this converges, it converges to 1, which I know is f of a. So now I know if this converges, it does converge to 1. That's what this helped me do. But now I just need my argument that this converges. And any argument I can think of to say that that converges requires me just showing directly that it converges to 1.
So just show it directly.
And that's basically the exact same thinking we did for how we constructed our subsequence.
So it's circular, is that what you're saying?
It's not circular, it just kind of made creating this subsequence. It's doing the same thinking as the subsequence almost, right? So how do I say that f of a converges? I say something along the lines of, I would say, something like, since the limit of, or since a is greater than 0, the exact same thinking we were saying up here, then there exists some index n in n such that epsilon be any number you want. Let epsilon greater than 0, then the absolute value of f of a n minus f of a is equal to 0, which is less than epsilon for all n greater than or equal to n, right? So that's the way I prove it directly.
How did we?
This, what is f of a n for all n greater than or equal to this index? 1 minus 1.
Oh,
Sorry, should have
Oh, I see.
said that better. So that's the direct way of proving it, which works. There's nothing wrong with it. It's the exact same thinking. I just thought that it'd be clearer to go create the subsequence and then show it this way, but yeah, don't know how to guarantee that this thing converges without showing it converges directly, which then you go through the exact same work you did creating the subsequence. So creating the subsequence might have been one of those things that sounded like a good idea and was really just not. But that works. There's nothing wrong with that. Anything you don't like about that? Do you feel like you understand the proof? And we just did for the case where a is greater than 0, obviously a less than 0. Then there's going to be a subsequence where all the terms are negative, exact same thing. So we only handle the positive case, but the negative case is identical.
This just feels different from how we usually prove there's a limit, because first we choose the index n, and then we get epsilon, where usually don't you do it the other way around?
Oh, it doesn't matter. I could say let epsilon greater than 0 to begin with, and then I'd still find this exact same index, because I just found the index where this difference is always 0. So I didn't need to come up with some clever way to get less than a positive number, because it's just 0.
Okay.
Right? I could have just as easily said let epsilon greater than 0. And then I could have said, I mean, if you might be unhappy with the skip I'm making from here to here. That's usually where a lot of our work goes in, right? Because then I have to say, I have to make, here's a, here's 0, here's a, epsilon some positive number, doesn't matter what it is. Well, let's think about it this way. I know that an converges to a, so since the limit of an is equal to a, I know that there exists, I'll call it delta so that we don't get confused with an epsilon. Well, no, then I can say there exists some index n such that, so you're right that it does go backwards. There exists some index n such that a minus, or a sub n minus a is less than a half, which would give us a sub n greater than 0 if we work with the inequalities for all n greater than or equal to n. And then I know, then I can say let epsilon greater than 0, then f of a n minus f of a is equal to 0 is less than epsilon for all n greater than or equal to that index. Same thinking once again. And then, obviously, if you switch the inequality, still basically the exact same thing, right? I just wish that there was a nice way to just say that this converges. without having to just show what it converges to.
How is this not a nice way?
Just more work.
I don't like that I had to go straight to the epsilon n definition of convergence. Feels like we build up all these theorems from that, and now I'm going clear back to my first definition. I mean, when in doubt, you should always be able to do that. But I would guess that there is a more clever way to think about this, so you don't have to go clear back like I did. And I'm just missing it. But nothing wrong with going all the way back. Probably works. Okay. Now finally, let's show that this sequence, or this function, this is a special function, I can't remember the name of it, but it has a special name after a mathematician. It has no continuous points, and look at what that function's doing. What it's doing is we're taking every number, if it's rational, we map it to 1, if it's irrational, we map it to 0. And so, remember that both the rationals and irrationals are dense in R, and you need to remember our theorem that said if a set is dense, if and only if, for any real number you pick, I can find the sequence in the set that converges to that real number. So the trick here is, if my number is rational, I'm going to create a sequence of irrationals that converge to it, and then the images won't match up. And then if my number is rational, I'm going to pick a sequence of irrationals that converge to it, and then my images won't match up. That's the big picture of what I'm doing. Did that make sense?
I feel like you said the same thing twice.
Oh, I meant to switch rational and irrational the second time then.
Okay.
You'll see it. It's pretty easy. The trick is to remember that theorem about dense sets. We did a theorem that a set is dense if and only if. A set is dense in the real numbers if and only if for every real number there exists a sequence in the set that converges to that real number. Right? And I think you have to do a proof something along the lines of for every irrational number there exists a sequence of rational numbers that converge to it. Or maybe you have to do the reverse, something like it.
I think we did them both. There's a sequence of rationals that converges to an irrational number from the other root.
Yeah, so we're basically going to do exactly what you already proved is the heart of this proof. So we've got some function, it gives you 1 if x is rational, and it gives you 0 if x is irrational. So we're going to prove it's not continuous anywhere. So 1, let A be any point in R. We have two cases. A is either rational or it's not. Right? 2, if A is rational, comma, then there exists a sequence, there exists some sequence AN in the irrationals such that the limit of AN is equal to A. How do we know this? No, since the irrationals are dense in R. This is the thinking that we're using to justify this line, right? Should have started with this line. Since the irrationals are dense in R, then there exists a sequence of irrational numbers that converges to a irrational number. So then, what's the limit of the image of f of an, or of an? Equal to?
0.
It's just equal to 0. An is a sequence of irrational numbers. Therefore, the image of the sequence is just 0, 0, 0, 0, 0, 0, 0. And so the limit of the image of the sequence is 0, is not equal to 1, is equal to f of a.
Not as easy as I thought it would be.
Yeah, Very straightforward. This is much easier proof. And then 4, same exact thinking. If A is not in Q, then there exists a sequence AN in Q such that the limit of AN is equal to A. Once again, we know this because the rationals are dense in R. And then same thing. Then the limit of f of AN, in this case, is equal to what?
1.
1, because AN is now a sequence of rational numbers, and the image of every rational number is just 1. So this sequence is just 1, 1, 1, 1, 1, 1, 1, 1, 1. The limit of a constant sequence is just whatever that constant is. In this case, it's 1. 1 is not equal to 0, which is what f of A is. Because A is an irrational number, and f of any irrational number is 0.
Is it supposed to be f of A or the limit of f of A?
F of A is just a number. So the limit of f of A would just once again be f of A, but it's just this. The thinking is the image, you're just taking the image of this. If this is true, then take the image of both sides. Is that true? Kind of, the image inside the limit here. Right? Does this being true imply the limit of f of AN is equal to f of A?
Right.
If this being true at some point A implies this is true, it's continuous at that point. That's ultimately what continuity says. If the domain's behaving a nice way, the image is behaving that nice way too. Okay, any questions on this proof? Therefore, it's not continuous anywhere, would be my last thing, but I think you see the proof.
Why is a famous function or whatever?
Because it's not continuous anywhere.
It's
In
just
most
like-
functions,
We have, so remember that we are working from foundations of math that weren't the same foundations of math that you would have worked from 200 years ago. We slowly worked down to what exactly it meant for a function to be continuous. If you went to Isaac Newton and you said, here's what a continuous function is, he'd say, what are you talking about? No, it's not. This is not the definition of continuity that he used. He had this idea of continuity that was a special case of this, that people found other ideas that seemed similar, and someone came along and said, you know what, actually these are both the same idea in some sense. And so things that then become kind of obvious or trivial were at one point a big deal. Does that make sense?
Yeah.
So this falls because we're working from very nice definitions and theorems that end up working to this. But math is kind of developed both ways. You have the intuitive math, like 1 + 1 is 2, and you work backwards to build up your foundations, and you work forward to build up the other implications that come from that. So the fact that we've worked backwards so far makes stuff like this all now nice and simple and easy. And we'll come across in topology, even more generic definition of continuity, and we'll see that this is just a special case of that. And so, foundations have been very well developed.
are there very few non-continuous functions?
I don't know how to answer few versus non-few.
Well, I
There's
mean,
infinitely many non-continuous functions. There's infinitely many continuous
you said that
functions.
this is a famous function because it's not continuous.
Well, it's a very easy to understand function that's not continuous anywhere. There's nothing hard for you to understand about what this function is doing, and it's very easy to demonstrate this function isn't continuous everywhere.
With most other non-continuous functions anywhere. Is it?
When you say most, in the context of infinity,
Right, I see your see the problem.
it's like, are most numbers even? No, they're mostly prime. Okay, that handles that. You can keep looking at that while I figure out the next thing I want to go over. We did that. Notation. Notation, what it means to add functions together, multiply functions together, divide functions. Pretty similar. Notation or definition? Let me look in the book. Did that. Yeah, definition. Alright, so some definitions. Given f is a function from D to R and G is a function from D to R, they've got to have the same domain. Yes. Our first definition, 1, we say the sum of f plus g of x is just equal to f of x plus g of x. For all x and d. This is exactly what you're used to. 2 f times g of x is equal to f of x times g of x for all x and d. And then we have our third one, which is division. F divided by g of x is just equal to f of x over g of x for all x in d, where g of x is not equal to 0. So our definition of division only works if g of x is never equal to 0. And then these definitions are exactly what you're used to. You've done stuff like this all the time. In fact, we've kind of already been cheating using these ideas a little bit. But you did this in like an algebra class. They said if f of x is equal to x squared plus 2 and g of x is equal to, 2x, then you knew how to do f of x plus g of x, you just add these together. You knew how to do f of x times g of x, you just multiply those. And you knew how to do f of x divided by g of x. But you had to do something special when you divided. You said where this isn't 0, so you had to restrict the domain to all the points that aren't 0. And then this worked. You remember doing stuff kind of like that? So that's all we're talking about there. This isn't anything new that you haven't come across before. It's just for the sake of making sure we define everything we're talking about. Okay, now what our proofs are going to be is that we're going to prove that if f and g are continuous, then this function is continuous, this function is continuous, and this function is continuous.
Is that multiplier composition right there?
Multiply.
Do we want to, do we define composition here as well?
Yeah, so next we'll define function composition, and then we'll show if two functions are continuous and their image and domain match up a certain way, then the composition of the functions is also continuous. So we're going to show that the sum of continuous functions is continuous, the product of continuous functions is continuous, the quotient of continuous functions is continuous, barring some condition, and then we'll show that the composition of continuous functions is continuous, barring some restriction. Good? That's a big picture of what we'll do. So let's do, I won't write down that we're going to prove it, we'll just prove it. Let's prove that if f and g are continuous functions, then all these combinations are continuous. Maybe we'll just do the sum, because once we show the sum, I think you'll get the rest of them. They just immediately follow from the fact that the sum of limits is continuous, the sum of product, or the product of limits is continuous. Sorry. Let's just do it, and then you'll see the rest. Geez, it feels like it's easier to just do than say. My hand works better than my mouth. All right. If f from D to R and G from D to R are continuous, and then F plus G is continuous. Notice F plus G is also from D to R is continuous. Understand what we're proving? Alright. 1. How are we going to show that it's continuous? We need to pick any point in the domain and any sequence that converges to that point and show that the image of the sequence converges to the image of the point. So let, what do we want to use? A, I guess we've been using. Let A be any point in D, and let AN be any sequence in D, such that the limit of AN is equal to A. Now, since F is continuous and G is continuous, what do we know? Since F and G are continuous, what do we know?
Well, we know that the limit of the image,
The limit of F of AN is equal to
F of A,
F of A, and the limit of G of AN is equal to G of A. That's what it means for them to be continuous. Right?
Mm-hmm.
Pick a point in the domain, pick a sequence that converges to the point. A function is continuous if and only if the limit of the image of the sequence is equal to the image of the limit. Okay. And then F, well, let's just do it all in one go. Then the limit of F plus G of AN is equal to, what's up?
Any students?
I'm not. The limit of F plus G of AN is equal to the limit of, use our definition of this, what is F plus G of AN? It's just F of AN plus G of AN, which is equal to the limit of a sum is equal to the sum of the limits. And then finally, we know that since this is continuous and this is continuous, that is just equal to F of A plus F of G, or G of A.
because it's continuous. Alright, okay.
Yeah, I already knew that this is equal to this, and this is equal to this, since those are continuous functions. Therefore, this is equal to this. Therefore, the limit of the image of the sequence is equal to, oh, sorry, let me do one more line here, which is equal to F plus G of A. There we go.
By definition.
Yeah, that's the definition of what this is. This is this. So, the limit of the image of the sequence is equal to the image of the limit of the sequence. And then I think you know exactly how we would do it for product. It's the exact same thing. Replace all your pluses with times, and we know that the product of two sequences is equal to the product of the limits of the sequences. And then, once again, for divide, all we do is make sure that g is a function where g is never equal to 0. Then we know that the limit of a quotient is equal to the quotient of the limit as long as the bottom part is never equal to 0. So I think you see immediately how the next two follow from this. You just replace the symbols.
So in order to prove the third one, you would just need to add that G also
Yeah.
can't ever be equal to
If
0.
f, d, and g is this, where g of x is not equal to 0 for all x in D, and is continuous, then blah, 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 blah. Because we had the same restriction when we talked about the limit of the limit of a quotient. So the limit of an over bn is equal to a over b if and only if, or this is only true when bn is never 0. Because if bn's 0 even once, then there's going to be a term in our sequence undefined. So we can't allow bn to ever be 0. Same thing up here. We can't allow g of x to ever be 0. Otherwise, there could be a point when we're taking the quotient of the two where it's not defined. Think you're good with these three? Do you think you can prove something like this on a test?
I have a question.
Yep.
So you said whenever bn is never 0, and I thought it was whenever the limit of bn is never 0, then the quotient works. But then I thought about it, and is there ever a sequence that converges and has 0 in it? Does it ever converge to something other than 0?
Sure.
Then what is that?
I mean, you could just make one up. You're overthinking it, trying to come up with clever patterns to write shorthand for sequences.
Oh.
But I could flat out make the sequence 0, 1, 1, 1. That was my sequence. First term 0, everything else is 1. It has a 0, it converges to 1.
Then isn't it whenever the limit of bn is never equal to 0, then that works?
No, bn can't be 0, because then this sequence is undefined as a term. An over bn is now a sequence. This is a perfectly valid sequence. This is a perfectly valid sequence. But then if I try taking this sequence that's a quotient of the two, my first term is 1 over 0. That's not a sequence. So I have to ensure that this thing is always a sequence, and the only way to do that is bn can never be 0. Similarly, I have to ensure that f of a divided by g of a, or f of an divided by g of an is always defined in order to talk about sequence. So that's what we know over here. We replace this with divides when we're doing the divide case. This is only defined if I'm guaranteed that this is never 0. The only way I'm guaranteed that this is never 0 if I know the whole function is never 0, because I don't have any information about this sequence except for that in the function.
I see.
Any other questions? Come to think of it, I think we did probably make that mistake when we went over it. I think I probably just said where b is not 0 when I should have said where bn is never 0. But I'm sure the book has it right. Oops. We're good? Actually, yeah. Okay. Let's see. Okay, so the next thing was to prove that next we're just going to define function composition. Then we're going to prove that, what did I put here? Oh, that's just my proof of that. Oh, I had a corollary. Okay, quick corollary. So we already proved that polynomials were continuous. You remember that? We're back to 2.1. We proved polynomials were continuous. Now I show that as long as the bottom function is never 0, the quotient of two continuous functions is continuous, right? Have you ever heard the term a rational function? Okay, a rational function is just a quotient of polynomial functions. So the corollary is just that rational functions are continuous if the denominator is never 0. So I know polynomials are always continuous. I know if I have two polynomial functions here then, and the bottom's never 0, then the quotient of two polynomial functions is a rational function. The quotient of two polynomial functions where the bottom one's never 0 is what a rational function is. So the corollary is just rational functions are also continuous.
In rational functions, isn't there often there's a jump, there's a shift. Like I'm looking at.
So yeah, so if we look at something like x cubed plus x over x minus 2, then you're saying, uh-oh, so here's f of x. So you had something like this in an algebra class, and they would tell you something like, so this right here is a rational function. They would tell you something along the lines of find the domain of the function.
Right, and it can't be 2.
And what they meant by that is find the domains that enable you to. They meant what's the largest subset of real numbers you can create and keep this defined.
Everything.
That's what they were saying. And so what you end up creating is you say, we have f is a function from, what's it from? It's from negative infinity to 2, not including 2, union with 2 to infinity, and it goes from that to the real numbers. Okay, so the function this, from here, from here to here, given by this, is now continuous.
So in that case, you're set. That's just d. So it is in fact continuous.
Yes, this is now a continuous function. Notice that this is rational. It's polynomial over polynomial, and the denominator is never 0. Rational or continuous.
Yeah.
So now we have, for the vast majority of functions you're used to dealing with,
They're all
you can now
continuous.
quickly say whether or not it's continuous, and the vast majority of them are that you're used to working with are continuous. Right? Okay, so now we just got to do function composition, prove that the composition of continuous functions is continuous, and then we're done. So, definition. Let f be a function from d to r. I think I'm going to do d to u, some subset of r. Oh no, I just specify that the image of d is a subset. Okay. So let f be a function from d to r, and g be a function from some set u to r, such that f of d is a subset of u. You understand what I mean by that?
No.
The image of f is
Yeah,
a
you're,
subset of the domain of g.
yeah. So f of d is a set of all numbers that f maps to. Let's do a quick example. If I have f of x is equal to x squared, what does this function look like? Just draw a picture real quick. It's just a parabola like that, right? So, let's see, how were you guys told it? You were asked to find what is the range of this function.
0 to infinity.
The range of this function, all the outputs, are anything from 0 up. All the numbers I can possibly get out of this are 0 or positive numbers. Does that make sense?
Okay.
So this function f, this is a function f from the real numbers to the real numbers, right? Ignore this stuff for a second. Just, we have f is a function x squared. So all its right-hand values, if we were to write this thing out, maybe this will help you since you took discrete math. If we were to write out all the things in this function, what's everything in there? Well, we have negative 2 goes to 4. We have negative 1 goes to 1. We have 0 goes to 0. We have 1/2 goes to 1/4. We have ... We have infinitely many things in there, right? And we can't write them all. right?
Okay.
So what we mean by this set is the domain. It's a set of all the left-hand values in our function. Graphically, it's a set of all the numbers here, our domain. All the x values, or all the left-hand values, if you think about it this way. So that's what we mean by this set. Whatever set is on the left, it's all our left-hand values. This set on the right, it's not the set of all our right-hand values, but all our right-hand values have to be in that set. So if f is a function from R to R, then we know that its domain is R, and its image, or its range, is a subset of R. All the right-hand values, if we put all those in a set, it's going to be a subset of this. They all have to be in here. But it doesn't have to use all the values in R.
Okay.
Okay? So, when we're talking about f of x equal to x squared, when we're talking about this function, what are all the right-hand values going to be? What are all the possible numbers I could get out of this function if I can plug in any real number I want? Well, can I ever get a negative number?
No.
No, so I can't ever get a negative number. Is there any positive number I can't get? No. So I can get every positive number, I can't get any negative numbers, and can I get 0?
Yeah.
Yes. So I can get all the numbers from 0 to infinity, not including, just say that. All the numbers from 0 to infinity, including 0, right? Which is why if you were to graph it, if you were to plot all those points, then they're always up here. They're all the positive numbers. If I take -2, it goes up to the number 4, right? Or if I take 3 over here, it goes up to the number 9. 9 would be how high it is here. Anyways, so that's what we mean. This is what we mean by f of R. I'm saying f of the whole set R, when I plug in the whole set R to my function f, these are all the values I get out. So we're saying, if I have a function, f and g, and f, when I plug in all the possible values that I can in g, get out of f, when I plug in my whole domain, all the possible values I can get out of this function are a subset of the domain of g. Not when, we're just saying that is the case. So an example here would be, I could have also made a function g, and g is from, not all the real numbers, but it's just from 0 to infinity, like that, and g, that to the real numbers, by, let's see, we'll say g of x is equal to the square root of x, right? Because we can only take the square root of positive numbers. So here's an example that fits our case here. We have two functions, f and g, and notice that the image of f of its domain, if we plug in the domain to f, we get this, is a subset of the domain of g. In this case, they happen to be equal. But equal sets are subsets of each other, right?
Okay.
Yeah, this is the toughest part in this section. This is getting function composition. Let's draw one more picture, way oversimplified, just a discrete picture to show another case of how this could be happening. I could have a set A, B, C, and we'll put in the set A, so here's the set, we'll make the set A, 1, 2, 3, we'll make the set B, 4, 5, 6, 7, 8, and we'll make C 9, 10, 11, 12, 13. So now I may create a function f from A to B by f is equal to. If f is a function from A to B, it has to map everything in A to something in B. So all map 1 to 5, all map 2 to 6, and all map 3 to 8. Okay, here's a function f from a to b. With me so far? And to draw in the values, we mapped 1 to 5 to get it very pictorial. 1 to 5, 2 to 6, 3 to 8. This is f. Good so far? Alright, and then we'll make a second function, g. G will make a function from b to c by g is equal to. Now, if g is a function from b to c, it has to map everything in b to something in c. So I'll map 4 to what? 10. I'll map 5 to 9. I'll map 6 to 10. I'll map 7 to 13. And I'll map 8 to 10. Okay, here's another function g from b to c. It maps everything in b to something in c, so it's a function from b to c. That's what that means. And now, let's draw it out pictorially. We mapped 4 goes to 10. We mapped 5 goes to 9. We mapped 6 goes to 10. We mapped 7 goes to 13. And we mapped 8 goes to 10. Looks something like that. This is G. So, notice that everything F maps to is a subset. Everything F maps to, what is that? Everything F maps to is just the set 5, 6, 8. Everything F maps to is just a subset of this whole set, 4, 5, 6, 7, 8. So it fulfills this condition. Sorry, over here we always have 2 to the real numbers because that's what we care about in calculus, is 2 to the real numbers. But I could have just made these arbitrary sets. Actually, this worked. We're still good. Because notice that these are all real numbers and these are all real numbers. So since I did everything with real numbers, we're still good. So F is a set not only from A to B, I could have also said F is a set from A to the real numbers. And I could have said that G is a set from B to the real numbers. Let's try and follow this as closely as we can. Right? It maps everything in A to something in the real numbers. And G maps everything in B to something in the real numbers. So now we have 2 functions, F from A to R, G from B to R, such that F of A is a subset of B. F of A is 5, 6, 8 is a subset of B. Okay, it's dense. There's a lot going on. Function composition, hardest thing to wrap your head around out of the operations we apply to functions. So now, we were doing our definition. Okay, so now we're going to define.
Wait, I have a question. How are F and G related here? Like, they're related over there.
F of D is a subset of U. That's the only connection. So over here, we said, let's even match how we have it written over there better. I should have done this to begin with. So we'll call this D, we'll call this U, and we'll keep that C, that doesn't matter. So now F is a function from D to R, and G is a function from U to R. And notice that now, looking at this, let's erase over here. Now notice that F of D is equal to what?
Okay, fine. They're still related though, because D is going directly to U. That's not necessarily the case here, right?
It is the case here. So F of D is equal to the set, what? 5, 6, 8. U is equal to the set 4, 5, 6, 7, 8. So we have f of d is a subset of u.
Right.
All the things d mapped to were in u. All the things f mapped to were in u. All the things f maps to are in u. So f maps something from d, wherever it maps it to, it turns out it is in u. So then g could then take it and map it from u somewhere else. So, let's see. We define G composed with F. G composed with F of X. Do I want of the X or do I just want? I think I will. Yeah. We define G composed with F of X to be G of F of X. That's what we mean by function composition. So, let's write it over here. Using this example, let's write exactly what G composed with F is. So over here, G composed with F is equal to for all x in wherever we started, D. Sorry. So, pick something in D, like 1. 1. What is f of g of 1? Or g composed with f of 1? That's g of f of 1. What is f of 1? F of 1 is 5, or f maps 1 to 5. So g of f of 1 is the same thing as g of 5, which is equal to, what does g map 5 to, or what's g of 5? 9. So now in g composed with f, 1 goes to 9. Same thing for 2. 2, what does 2 go to? 2. F of 2 is 6. G of 6 is 10. So 2 goes to 10. And then last one. What does 3 go to?
10.
It also goes to 10. Perfect. There we go. So that's F composed, or G composed with F. Or a typical way that we read this is G after F. You apply F to the number first, then you apply G. So I'm reading that, it's common that you say G after F. So that is function composition. Let's do function composition one more time with functions like these types of functions that we're used to. So let's say that f of x is equal to x squared plus 2. And let's say that g of x is equal to, I don't know, x minus 2. Something like that. So let's look at g composed with f of x. Well, g composed with f of x is the same thing as just g of f of x. When we plug in f of x for g, we would just plug in whatever f of x is for all the x's. So that's equal to f of x minus 2. We plugged in f of x for x in g. So we plug in f of x for x, but what is f of x? It's x squared plus 2. Good? Similarly, let's look at f composed with g of x. In this case, we're looking at f of g of x, which is equal to, plug in g of x plug in that for x in f of x, and we get x minus 2 squared plus 2. And notice that those are very different things, right? This top one simplifies to just x squared. This bottom one, we're going to get x squared minus 4x plus 6. Right? So order matters in function composition. F composed with g and g composed with f are not the same thing. Notice over here, we could do f composed with g, but g composed with f doesn't make any sense. I can't use g to map these numbers to these numbers, and then use f to map them again. F can't use any of these as inputs. So f composed with g and g composed with f are very different things. Don't think that you can swap the two around. Alright, so let's do our final proof. Our final proof is that if f and g are continuous functions that satisfy this condition so that we can compose them, then their function composition is also a continuous function. So let's prove it. Oops. Proof. If f is a function from d to r and g is a function from u to r such that f of d is a subset of u and f and g are continuous, then let's see, we're going to do g composed with f. G after f from d to r is continuous. Alright, let's prove it. 1. Let f from d to r and g from u to r such that blah blah blah, everything up there. Such that f of d is a subset of u and they're both continuous. Now, remember what we're trying to show. We're trying to show that this function right here is continuous. So I need to grab some arbitrary point out of its domain as a sequence that converges to that point, and then show that the image of the sequence is equal to the image of the limit. So 2, let A be any point in our domain, and let AN be any sequence in D such that its limit is equal to A. Right? 3. Then, how do I want to say this? Let's just kind of do it in one go, explain as we go. So then the limit of G composed with F of AN is equal to, should we do this in one bite at a time?
No.
I think I kind of need to, otherwise we'll be cramming it. So then we know that the limit of, here's how I'll say it. Then the sequence f of AN is a sequence in U, comma, and the limit of f of AN, sorry, let me switch markers, and the limit of f of AN is equal to what? How do you know that?
Because of the definition of continuity.
Yeah, because f is a continuous function. And that is also in U. Alright, so let's make sure you understand what we're saying here. Remember, we know that the image of f is a subset of U. So everything f maps to has to be in U. So f of an, whatever this sequence in, has to be in U. And f of a, whatever this is, has to be in U. So now we have f of an, a sequence in U, converges to f of a point in U. Then, we'll just say then the sequence G, now I think I can do it all and let you see it. So then the limit of G composed with f of an is equal to the limit of, remember, G composed with f of an by definition is just G of f of an. That's not, we'll combine that all in one go here in a second. Here's what I want to say now. I'll just write it like this. Maybe this is the best way. Since G is continuous, and since f of an not and since, we'll just say then. Since G is continuous, then the limit of G of f of an is just equal to G of f of a. Okay, that's the leap I was trying to make, but I wasn't sure how best to do it. This makes sense. Why do I know I can do this?
Because G is continuous.
Because G is continuous, and what is f of an? It's a sequence in its domain. G is from U to R. I know f of an is in U, and it's a sequence in U that converges to f of a, which is in U. A function is continuous if for any point in its domain, and any sequence that converges to that point, the image of the limit of the sequence is equal to the image of the limit of the point. Here's a sequence. Here's a point. I know that this sequence converges to this point. Therefore, the limit of this sequence converges to this point.
Missing the logic.
Okay. Let's do some renaming. This is what I should have done. Kind of done that. 4. We'll just say that. Let Bn equal f equal the sequence f of an.
Oh, okay.
And let B equal f of a. Since G is continuous, G, the limit, can't get a good marker, that's the red. Then the limit of G of Bn is equal to G of B, so that's logically equivalent to, well, I'll just do implies, doesn't matter, that's logically equivalent. That implies that the limit of G of f of an is equal to G of f of a, which gives me the whole crux of the proof, the limit, or the finishing touch of the proof, of G composed with f of an is equal to g composed with f of a. And we're done. You follow the steps there? I should have just done that relabeling to begin with. That clears up all the confusion of what I was trying to say.
Yeah.
That this is just another sequence that converges to just another point, and that these two are now in U. So we start out with a sequence and a point in D, and use that to construct a sequence and a point in U, and then the whole thing together is continuous. Any questions on that? Okay. And that's the end of 3.1.